I appreciate that you, I hope, all come to see the full audience, still full audience. Yeah. Okay, so let's just continue the discussion of BEC in the ideal Fermi gas. And now I want to present you what was a big issue in, I guess, 70s or 80s, what is called off-diagonal long-range order. Off-diagonal long-range order. Sometimes you will see this abbreviation off-diagonal long-range order. What people discuss whether it's necessary for the superfluidity and sufficient condition, etc. But we will see now that it's not directly related things. And well, this is kind of very scientific name. In a simple form, to demonstrate this in a simple form, let me calculate, okay, in a condensed matter language correlation function. In the quantum optical maybe sense, it's a density matrix. Let me correlate this. Let me calculate this correlation function C R1 R2, which is just the average over whatever equilibrium state at some temperature T of these things, R1 and psi R2. Or maybe let me do it 2 and here 1. Yeah. So you annihilate particle at position R1 and then create it at position R2. Or in other words, what it says, it's actually, it is overlap between the states psi R1 and whatever, and psi R2 and whatever here you have density matrix or thermal state or pure state. Yeah. So this is density matrix or correlation function. So to calculate it, let's come back to our expression for the psi field, for the field operator. And of course, in our case on the box, let me explicitly, we know the BEC, it's something about the zero momentum state, a particular importance of this state. Let me write it A naught divided by the square root of volume plus 1 over square root of volume, and then we have sum over all p not equal 0, and then we have AP, and then we have the plane waves. So now I just want to plug it in and take the average, and of course the off-diagonal term disappears. Yeah, so if I just continue my correlation function, so here CR1 R2, yeah, that's what you will find. So you have an average of A0 dagger A0 divided by volume, yeah, plus 1 over volume, sum over P non-zero, and then you have AP dagger AP, and e to the I over H bar P R1 minus R2. As I said, off-diagonal term will disappear. Yeah. So now it's clear. So now we continue. So this gives you number of particles. This is number of particles operator. Yeah. So now we will have n0 divided by volume. Yeah. So number in the condensate divided by volume plus, and here we just have our Bose-Einstein distribution function. Yeah, for our particles. So it's 1 over the volume, sum over p, e to the not equal 0, I over h bar p, let me call it r, just for r is just r1 minus r2, just to make it shorter. And then we have this Bose-Einstein distribution, Bose-Einstein. Yeah? And so now this is a very general statement, and it's valid above TC and below TC. Above TC, of course, this term vanishes, and here we have mu. Below TC, this term present, and so here we have zero chemical potential. So let's now just calculate in these two cases. Case number 1, T less than TC. Yeah, then what we have to calculate is C of R is just N0 of the volume plus the sum where now I have e to the I over h bar pr, and now here I have e to the, okay, p squared over 2m minus 1 over t, yeah, minus 1. The mu is 0. Yeah. So of course I will be interested, would be interesting to see how this function behaves for r goes to infinity at a very large distances. Yeah. So normally we think that in the so to say normal system, the correlation between different parts of the system decays when these parts are separate by larger and larger distance. Yeah? So of course this is no problem, it just stays like this. So to calculate, to estimate this integral, yeah, we have to remember the basic about the basic facts about the Fourier transform, that if we want to have large r here, then the dominant contribution comes for small p. Yeah. So therefore we need p, that is the main contribution, comes from a small p, where we just can expand the exponent, yeah, and one cancels, so what we end up would be this, let me call it n0, yeah, concentration of the condensate particles. This is these things. And then of course, according to my table, the sum replaced by the integral, so we have this integration, and this is r goes to infinity, yeah, and h bar cube. And here, if I expand, yeah, to the first order, one cancels, and this I have inverse. Yeah, so I will have 2mt over p squared e to the I over h bar pr. And this integral you, of course, know. Yeah, do you know this integral? It's from the classical electrodynamics. Sorry? What is the Fourier component? This is actually 1 over p squared up to some 4 pi. It's a Fourier component of the Coulomb potential. Yeah. So if I use this, so what I will get here, 2m t over, I need from here h bar squared, and I guess it should be something like 4 pi, oh no, 1 over 4 pi r, big R. That would be the answer. Yeah. So what you see here, it actually, when r indeed goes to infinity, it goes to n0. So correlation between different parts does not decay. Yeah, they stay constant, and this constant is determined by the condensate fraction. And this is exactly what is called off-diagonal. Off-diagonal because in the density matrix, if I consider R1 and R2 as the entries of my density matrix, this is off-diagonal elements. Diagonal is R1 equals R2, but that would be the full density, of course. Yeah? But off-diagonal R1 not equals R2, and actually very far off-diagonal. Yeah? So the distance goes to infinity, and then you see it goes to constant. So let's see what happens. This is exactly these things. So now let's consider the second case, t larger than tc. Then, of course, we don't have the first term. In our correlation function, c of r becomes now just a sum, of which I again replace by the integral. So I have dp 2 pi h bar cube e to the I over h bar pr, and then I will have e to the p squared over 2m, okay, plus modulus mu. Remember, mu is always negative, minus 1. Yeah. So let me be not very far above tc, but let's close to tc. When mu actually goes to 0, actually it's a good exercise, but you need to be very skillful in analytics and calculating integrals, how mu approaches 0 when he approaches to tc. If I remember correctly, that should be like t minus tc squared. So then, but anyway, this is larger than Tc, mu approaches 0, we assume that this is small, ratio mu over T is small. Yeah, and then of course if we again interested in the large distance behavior, then P goes to 0, so all this argument of the exponent is small. We again do the same trick as here, we expand, and then what we get is the integral dp over 2 pi h bar cube, and then we have this T now divided by P squared over 2m plus modulus mu e to the I over h bar PR. So now let me do the following thing. So I just have this 2mt divided by h bar squared, and then I will have, no, h bar comes later on when I just 2mt. And now I will have integral, and then e to the I over h bar PR divided by P squared plus 2m modulus mu. And now it's again something which you should be familiar with this integral. Who knows what it is? What kind of potential? With one of the P squared, it was a Coulomb potential, but one of the P squared plus kappa squared, what is this? Yukawa potential, right. So it's Yukawa potential. So what you get here, actually this same 2mt, now we have 4 pi here, h bar squared, yeah, but now we will have 1 over r e to the minus kappa r, where kappa squared is square root of 2m modulus mu divided, okay, 1 over h bar, and then square root of 2m modulus mu. So you see in this case, correlation decays exponentially, and this exponent is controlled by the modulus of the chemical potential or by the temperature. Yeah? As I said, chemical potential is a function of temperature. So you see you have a, and then of course when we approach the transition from the high frequency, from the high temperature side, you see that this goes to 0, and of course we recover our previous expression. Yeah? So you see that below Tc you have something interesting that comes. The question is whether it would be sufficient for superfluidity or not. This question we will answer a bit later. But before going to this and preparing ourselves to answering this question, because it requires some special way of, well, not special, but particular way of thinking that becomes especially simple. Let me discuss, briefly discuss with you BEC in under different conditions. So BEC under different conditions. So under different conditions, I mean that if we are 3 dimensions, what happens if we're in 1 dimension, in 2 dimension, in 4 dimension, or what happens if we are considering not the infinite system, or what we consider infinite box, but just confined system. Of course, then transition has to be, it's not a transition, it's a crossover, so it has to be properly, well, from a physical point of view, defined. I guess mathematicians will never give a definition in this case. Yeah. So, but anyway, so let me just to remind you how we start. We all start with this, remember, with this sum, yeah, where we have this the sum of all particles in our state, single particle state, and it was our starting point for the BEC. And then we just have a look whether we can fulfill this without occupation of microscopic occupation of a single state or not. Yeah. So let me now consider a system where it's sort of, it has some energy level, single particles, or maybe epsilon, better say, yeah, not to miss with the total energy. So this is single particle eigen energies. And let me assume that they are larger or equal than epsilon 0. Yeah. In a trap, we know that it's h bar omega over 2. But in a box, it can be 0. or whatever 1 over L squared, depending which condition you use. But let me now choose epsilon 0 is, let me call it N0 for energies. Yeah? Yeah, so I just count all my energy variables, single particle energies and chemical potential, started from a 0. Let's just make a formula easier. Yeah? So now what we just have here, yeah, so therefore we have a sum over nu, and then we have this 1 over e to the epsilon nu. And remember, the critical was that we have, okay, let me write it like this. And the question was whether we can satisfy this condition by choosing mu. Yeah? In a 3D, we see that below some temperature we cannot. And that's why we need here some extra term, occupation of the zero momentum state. So let's see how it works in this case. So of course, it is convenient to rewrite these things. You see, it depends only on the density. Yeah? Sorry, depends only on the energy, not on the actually, not on the particular quantum numbers. So it's just what matters from a single particle state and its energy. So that's why it's convenient to introduce the density of states again. Yeah, we introduce density of states. Sorry, it's the same index. So, okay, should I? You won't be confused, yeah? Okay, let me write here. This is density of states, so number of quantum states in some unit interval of energy. Of course, if you have a continuum spectrum, like we have in an infinite volume, or in an infinite surface, or an infinite line, this integral is well defined, yeah, because we know integral of a delta function, how it operate with. But if you have a discrete spectrum, that this is typically, if you look on the right-hand side, this is kind of strange object. Yes, so it's almost 0 when you hit the eigenvalue, eigenenergy is just infinity, and then again 0, and then so what then people think in a discrete spectrum, that means you count actually the levels in some energy interval, which is much larger than the level spacing. Yeah. So you kind of replace these well, strange function, this sum of this delta function, in kind of you smoothen it over some interval delta e, which is much larger than the distance between the peak of the you will see why it would be sort of this kind of quantity would be relevant in this case. Yeah. So therefore, with using this quantity, you can replace it with the integral over energies from 0 to infinity. 0 is because, yeah, there's 0. Otherwise, you have to start with epsilon 0. And here you will have 1 over, so g on epsilon, oh, sorry, nu on epsilon, divided by e to the epsilon minus modulus mu divided by t minus 1. Yeah. And the question is, of course, remember how we deal with the BC. Yeah. So it's just whether this integral is finite for mu equals 0 or not. Yeah? Because if it's finite, then we cannot put more particles than we already have, and we need to add some macroscopic occupation of a single quantum state. But if I set mu to 0 and the integral diverges, that means whatever n is here, I can always find the solution for mu. Because if I set mu to 0, I get infinity. So if my mu modulus mu is non-zero, I get some number, and when I derive my modulus mu from something to 0, this n ranges from some finite value to infinity. So I can always fulfill this condition. So the question is BC or no BC. Yeah. It's actually BC or no BC. It is equivalent to the statement diverges or not diverges. Converges or diverges. Is it clear what I said? I give some examples. Yes? Sorry? Should it be?
In the integral is the density of state.
Yes.
The denominator shall be epsilon plus.
Right, sorry. Plus modulus mu. Right. Thank you. Yeah. And then, of course, you see then the question converges or diverges for modulus mu is 0. It's a question how this density of states behaves when nu goes to 0. Yeah. So from here, you immediately see, because if I set, and I want to have t non-zero, no? Because as I said, t equals 0, ideal Bose system is always Bose condensed to the lowest eigenstate. Yeah. BC or no BC, let me make comment for t with, they better say with, TC non-zero, and moreover TC larger or better much larger than this level spacing. We are not interested in the case where the TC is, let's say, half of the h bar omega in the harmonic trap, but we're interested in the macroscopical critical temperatures, which are much larger than the level space in the harmonic trap, just h bar omega. Yeah. And of course, then we have to analyze this integral. So again, when modulus mu is 0, this goes to 0, this finite. Yeah. So we just have to analyze the convergence of this integral, d epsilon divided by epsilon, nu on epsilon, at small values of epsilon. Yeah. So namely, this integral converges or diverges. And then, of course, you know the conditions. So that it converges if nu on epsilon behaves like epsilon to the alpha, where alpha is positive. Yeah? Because alpha is 0, so you have a constant, yeah, or logarithmic. It's also kind of 0 power. Logarithm is also 0 power very often. Then you have a logarithmically divergent integral, and that's exactly what happens in 2 dimensions. Yeah. But if nu on epsilon goes to 0 with some power, yeah, goes to 0, yeah, then it converges, and then you have BC. Then in this case, you have BC. So let me give you examples here. Yes, you always have convergence if you have integral. Then you get it like this. Yeah. The epsilon over square root of epsilon is square root of epsilon.
Yeah, but I mean,
Alpha 1/2 is a 3-dimensional case. Okay. So a few examples. First, I start with a box. Yeah. D-dimensional box. Then, of course, our density of state, and here we're interested per unit volume, would be just dp, ddp, yeah, 2 pi h bar to the d, and then we have delta epsilon minus p squared over 2n. Yeah? So, of course, here you can just continue. So here you will have angular integral give you some a volume or area, or whatever you call it, of a d-dimensional sphere, just 4 pi in 3 dimensions, I guess 2 pi squared in 4 dimensions, and 2 pi in d phi, yeah, in 2 dimensions. Yeah. And then the integral, it's at dp, p d minus 1, and here you have delta epsilon minus p squared over 2m. Yeah. And then, of course, you can easily make it like this. So you write it p d minus 2 and m d on p squared over 2m. Yeah. If I take a differential, I get p dp divided by m. M disappears. Yeah. And then this one, so you have omega d, 2 pi h bar to the d, and here you will have integral, let me call this now epsilon p, just to distinguish from epsilon. So you have d epsilon p, 0 infinity, that's this one. Then you have m here, it's this m, and here what I do the following thing. I will write it in the form of p squared of, sorry, epsilon p, 2m epsilon p to the power, that's exactly p squared. And now I put d minus 2 over 2. And then I have delta epsilon minus epsilon p. So now I can easily calculate the integral, right? Because I integrate over epsilon p, and here epsilon. Yeah? So, and this just give me omega d, 2 pi h bar cube. And here I will have m, and I will have 2m epsilon to the power d minus 2 over 2. Yeah. This is density of state in a box. And now we see the very famous results. Let's say d equals 3. Nu on epsilon scales like square root of epsilon, right? 3 minus 2, 1 divided by 2, 1/2 square root. Yeah? And now we have BC. So, yes?
There shouldn't be 2 pi h bar to the top.
D, yes. I'm so used to write 3, so sorry. Yes, and now we have 2 dimensions. And now you see that the density of states is constant. Yeah? 2 minus 2, yeah. So it's constant. So therefore we have this integral logarithmically diverges, so we can always fit the number of particles by choosing appropriate mu. I give you the formula. No BC. At finite temperature, right? Again, at these temperatures. At t equals 0, you always have, in ideal Bose system, you always have BC. We are not interested in this very, very special case. And now you have d equals 1, nu on epsilon. You know this, it's 1 over square root of epsilon. And it's even worse. Yeah? So we have no BC. So, meaning no BC, you can always fit. You can always satisfy this equation by appropriate. No, this converges, and then we have BC. If the integral converges with the square root itself a half, integral converges, we know it, we calculated it. So we have BC in 3 dimensions. In 2 dimensions, in 1 dimension, integral diverges. Here logarithmically, here like 1 over square root. And here we have no BC. And saying no BC, I have to give you, of course, the solution for the chemical potential, which is for this case. And so here, the chemical potential scales, you can always find the chemical potential in this form. This means some numbers. it is t e to the minus t0 over t, where t0, yeah, it is something like h bar squared over m and two-dimensional density. Yeah? You see, you can always satisfy this equation by choosing this value of mu. Yeah? So therefore, there is no BC. And in this case, in the one-dimensional case, modulus mu is simply scales like t squared over t0. And with t0 is, of course, h bar squared over m and one-dimensional density squared. So this is some characteristic temperatures or energy scales in this case. Yeah? Something like T star in our systems, in two-dimensional, three-dimensional, when the de Broglie, yeah. So it's roughly interparticles separation. So this is the behavior. You see, when t goes to 0, in both cases mu goes to 0, and that's we know at t is 0, strictly 0, all particles sits in the lowest energy state. So now, finally, what I want to discuss is the harmonic oscillators. Harmonic confinement. So now I have not a box, but d-dimensional harmonic oscillator. Of course, there you have, it's now this story about calculation of the density of states becomes this relevant, yeah, because you have a discrete spectrum. But if you are interested in TCs, which are much larger than the h bar omega, and that's exactly what we are interested in, then of course you see that this h bar omega divided by t is a small constant, small value, and in principle summing over n oscillator numbers, you can replace with the integration over n h bar omega divided by t, which is a small value. So I will not repeat here this kind of formal exercise replacing by sum. I hope in the course of analysis you had this chapter replacing sums with the integrals. Yeah. So here we just have to calculate the density of states for the harmonic oscillator, and in this sort of density of state, let me put it tilde, yeah, because we're interested here not in this sum, yeah, but sum actually, what you can do, you can write here like this, yeah, and here you sum with the, and the constraint that epsilon minus epsilon mu is smaller or equal than delta E. So you sum over all energy levels within some interval, and then you divide by this interval. That's what you actually would get. And then you get this, let me call it delta mu tilde. And then if you do some algebra, you end up with the following thing. Yes, so, okay. So you can convert this into the following thing. So here you'll have energy to the power d minus 1. And here you will have product over all I and h bar omega I. And then the numerical coefficients would be like this. You integrate over some variable y with this constraint. So this is the volume or area of the simplex. You are limited by unities. So you have d-dimensional space, and then you have unity on each axis, and then you have the kind of, in 2D, it's these things, 1, 1 in 3 dimensions. It's this triangle, etc. Yeah? So it's just a number. So you see, so these in D equals 3, nu on epsilon scales like epsilon squared. Yeah, and we have BC. So that means there would be some TC, yeah, which of course not strictly defined like in the box in the thermodynamic limit, because these transitions are thermodynamic properties. So here you will have crossover. you have to make some choice of your definition. Yeah. How would you define TC? When, let's say, on the lowest energy, I don't know. So I don't know. So 1/10 or so, then it's TC. Yeah. V equals 2. So here, nu tilde on epsilon scales like epsilon. And we do have VC. So in two-dimensional harmonic oscillator, in contrast to two-dimensional box, we have VC. And now d equals 1. Here we don't have BC because now it's a constant. And we have no BC. So you see this phenomenon is kind of very sensitive to the dimensions, to the confining potentials, etc., etc. So, but yes, so what you have to do is just look at the density of states. So there's nothing, because again, it's a BC or no BC, it's just whether you can satisfy this or not. Yeah? So it's nothing to do with interaction. Yeah? So now, now let me sort of prepare you to the discussion of superfluidity. Let me now have a look at this bosonic ideal Bose gas from the condensed matter point of view, namely what in every condensed matter books or consideration what you're looking for, of course what people discuss, what's the ground state, and what are the excitations. Yeah? So in this case, ground state is just reformulating of what you already know in a conventional language. Ground state, that means t equals 0. Yeah, that's the ground state. Yeah? And in this case, of course, we have condensate, all particles. In this case, we have n0 is n. And if I want to say my ground state, G, I just have a0 dagger to the power n divided by square root of n factorial and acting on the vacuum state. I just populate, I put all the particles in the state with p equals 0. Trivial things. Yeah? And this we know. Now look at the excitations. How we can excite this ground state, that's clear. Elementary excitation when you kick one particle from p equals 0 to some non-zero p. Yeah? Single particle excitations, we don't have any other. Yeah, so this is all trivial, so sorry for bothering you with this one. So therefore, we have A0 in a condensate, we have one less, and we create a momentum P. Yeah, that would be our single particle excitations with momentum P. It's clear how to create 2, 3, etc. Yeah? An important point that the energy of this excitation is epsilon P is P squared over 2m. Yeah? And momentum of this excitation is just P. And this one would be very crucial for absence of superfluidity in our system. So let's now discuss superfluidity. And this is based on what is called Landau criterion. Why I discuss all these things? Yeah, let's have a look at this superfluidity of frictionless flow from the point of view of this condensed matter. Yeah? So we now create a flow of liquid, or gas in our case, or whatever. Yeah? And the question is, of course, in the real situation, it goes into a tube, vessel with some non-ideal surfaces, etc., etc. And then the question is, how we know? So normal liquid will stop. But how you could describe the process of this stopping of this motion? Yeah, it is creation of excitations from a condensed matter point of view, creation of excitations with momenta which are opposite to the momentum of your system. Yeah? Because in this way, you take the momentum out. Yeah? If you create the excitation with momentum opposite to you decrease. Yeah? So the velocity decreases, then you create another one, it decreases, 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 and in the end it simply stops. Yeah? So we call it friction, yeah? But it's actually, from a condensed matter point of view, it creates excitations in a system. But when it's possible, of course, when the energy decreases. Because otherwise it would be very nice. Huh? You create a flow and it goes faster and faster and faster. So you just don't, it goes slower, but the energy increases. Huh? That would be a source of energy. Huh? We shouldn't go for the demonstration on Friday and miss the school, etc. Yeah? So therefore, the question is whether creation of excitations is favorable, energetically favorable, or not. Landau criteria is exactly tells you for which branches of excitations, under which conditions, it is favorable, meaning that you decrease the energy of the system, of your flowing system, or not. To get this, to formulate these criteria, let us consider some tube. Let's consider some system. In our case, it's ideal Bose-gas. But you can think about a generic system that goes. And we need two reference frames. So system is going with velocity v, let's say in this direction. So we create a flow. And then, of course, there is a reference frame k prime. Let me call it k prime, that goes exactly with the liquid. Why we need this? Because in this reference frame, system is at rest, and we know everything about it. Yeah? So in this system, let's say, in this reference frame, system in the ground state, and we know what are the dispersion of our excitations. For ideal Bose-gas, it's this. Yeah? Because in K prime, we know all about our system. And the second one is K, which is just our laboratory frame. Yeah? So now let's see if let's compare whether we gain or we lose the energy if we create some excitations. So let's say before, it's where we don't have excitations. Yeah? So therefore, in K prime, we have energy of our system as simply the energy of the ground state. And I forgot to tell you, but of course, you also know that the energy ground state in this case is 0, right? Because all momenta is 0. And total momenta of our system is also 0. It's at rest. Yeah? We assume it is in a ground state. In K, if you want, what you have, in this case, energy would be just E0 plus, if I look at the, mass over 2 volume squared. That's kinetic energy of my liquid. This is not that much important. So now and now we create excitations in K prime. We create excitations with momentum P and energy epsilon P. Yeah? So therefore, the delta energy here primes, refer to primes, would be change my epsilon P. Yeah? I create excitation, so I just increase my energy by epsilon P. Yeah? So here, exactly, I add one particle from, and change of momentum is, of course, P, the momentum of these excitations. Yeah? So now I have to recalculate these quantities to the K frame. In K, delta E, now you have to use the Galilean transformation, and that would be epsilon P plus PV. That's my increase of my energy in my K frame, in a laboratory frame. Yeah? And clearly, I can create if delta E is negative. Then I can create my excitations. Otherwise, it's energetically not favorable. Yeah? So let's now have a look. What are the conditions for this one? Of course, the most favorable case P, when P is opposite to V. Yeah, that's what we expect. Yeah, see, liquid should slow down. Yeah, you have pump momentum which is opposite to velocity. Yeah, so you take the momentum out of the liquid. Huh? So therefore, in this case, let me continue here. Delta E for this case would go into epsilon P minus P dot V. Yeah, and the question is, when this is negative or positive, with what we need, yeah, or positive, it depends on this thing. Yeah. So let me define this object, let's call it critical velocity, as a minimum over all P, epsilon P divided by P. Not a derivative, but a ratio. Yeah? So now you see, you can very easily look at this, if with this definition to this expression. If V is smaller than Vc, then delta E is always positive. Energetically is unfavorable, no excitations. So liquid will flow, and the energy does not allow excitations to be created to slow down, which slow the liquid down. Yeah? So this is if, and then for V larger than Vc, you can have, of course, in some part of your spectrum, delta E can be negative, and you start creating excitations. Yeah? So this would be superfluidity, superfluid flow, and here you will have friction. No superfluid flow. Of course, what happens in this case, yeah, you create some bunch of excitations, you slow down the liquid up to Vc, and then the process of creation excitation stops. The system will continue moving. Yeah? So let's now have a look in our case for the ideal Bose gas. So this is ideal Bose gas. In this case, so I would say, so here it's also in a more general system, like the ideal Bose gas, you have just a single particle excitation, so just a single branch of single particle excitations. Yeah? In an interacting system, you could have more excitation branches, single particle, collective ones, etc. Yeah? So you have to also look at all branches of this. Yeah? And it's actually in superfluid helium, there's not a phonons that limits the superfluid velocity, rather than ring excitations which you create with some edges, etc. Yeah? Ideal Bose gas, epsilon P is P squared over 2m, and therefore critical velocity is 0. Whatever, yeah. So at any velocity, you will get excitations that slows the ideal Bose gas down. So system is too fragile to be a superfluid. Yeah. It's this bunch of low energy excitations that you have with P squared over 2m that actually breaks the superfluidity, so in this case. Although we have a very nice Bose-Einstein condensation, their macroscopic wave function, but this function is so fragile that any perturbation actually destroy it. Yeah? It's not destroy it, but actually destroy the superfluid flow. You cannot have stable superfluid flow. It always stops. Yeah? And in the end, if you take the heat out, they all go to the P equals 0. Yeah? state. You will have a condensate but at rest. Yeah. So now the question is, and of course, yeah, let's see if we add interaction how the system changes. Yeah? Because, well, BEC alone cannot explain you the superfluidity, which is experimental fact, and physics is an experimental science, so we have to accept what all the theories has to accept what experiments tells us. So now, therefore, we have to go to somewhat more realistic. Yeah? Because ideal Bose gas, where do you have it? Yeah, you can have phonons. Yeah? Not exactly, because phonon can be absorbed and emitted. And also, if you go to quantum electrodynamics, there is interaction between phonons. In the fourth order, you will find some interaction between phonons. Yeah, but in atomic gases, it's of course clearly you have short-range interaction. So now let me take weakly interacting Bose gas. Now we have this G, which is 4 pi in most of the cases A, and of course you will see why we consider it positive. Because negative, it's a collapsing system, it's not a stable system, at least in a box. I guess physically clear. Yeah? If it's attractive, it's favorable to put all bosons on top of each other and decrease the interaction. So we take a repulsive case. Yeah. So now we come back to our Hamiltonian. And we try, it's already simplified, but still it's too complicated to be solved, except for maybe one-dimensional case where you have some special features, but not in 2 and not in 3 dimensions, yeah, which are the most interesting cases from the experimental point of view. So now let's see how this interaction actually modifies our system. And of course we will consider weakly interacting gas means that if I take n and take Na cube, yeah, so number of A is a scattering length, or without kind of Feshbach resonance situation, it's typically the same as the size of your atom. So if I calculate the number of atoms in the volume of the interaction range, I get very small number. Yeah. So that means collisions are rare, and yeah. So how we can use these things, the fact that the interaction is weak, how we can use it to solve the problem, at least in a low energy sector. Yeah? So this was called the Boголюbov transformation, etc. That's not the general solution of the model, yeah? Of this model Hamiltonian. It's a solution for the low energy sector. So it's just a corner of the Hilbert space, which of course is the most physically interesting. Yeah? Because we are not interested in the case where all atoms have a large momentum moving like crazy, so there is no structure in the state, no interesting properties. Let's look at the low energy physics. And how we can solve it. Yeah? What are the ideas? If G equals 0, so let's look for the ground state. Yeah? Again, the same strategy, ground state and excitations. Yeah? G equals 0, we know that the ground state is just this BEC. Yeah. So that means that momenta here, which are momenta here, all particles are 0. But now what happens at G non-zero? Of course, you have collisions. Yeah? So now you can take two particles in the condensate. Let me symbolically write it like this. P equals 0, that's one particle, plus P equals 0, that's another particle in the condensate. They collide. Yeah, remember this nice picture. So now I have P equals 0, P1 equals 0, P2 equals 0. And then, because I have here Q that goes, yeah, I can have P1 plus Q equals Q here, and P2 minus Q equals minus Q here. Yeah? So then here, after collisions, I will get Q non-zero plus minus Q non-zero. So that is what is called depletion. Yes, interaction, collisions, deplete particles from the condensate. So then they get P and minus P. Yeah. But of course, in the case of the weak interaction, we can assume, and it's a good assumption, that the number of these particles is small. So still a macroscopic number sits in a condensate. So in this case, of course, you can say that N0 is not N, yeah, because you have a depletion from there. Yeah? This, of course, is a dominant process, because you can say, well, these particles also collide. Yeah? Yes, of course, you're right. But here, if you remember the matrix element of the bosonic operators, yeah? So here, all the matrix elements for these collisions will involve square root of number of particles in the condensate, yeah? Which are very large compared to number of particles of order 1 here. Yeah? So these also collide, but the value of these collisions is extremely small compared to these processes, yeah? Because of bosonic enhancement, square root of N0. And we will use it in simplifying this Hamiltonian to the form which we can solve, to the quadratic one. Yeah? But N0 is very close to N. And of course, here we use this, that the collisions are small in this sense. Yeah? So NA cube much less than 1. We will check it afterwards. So these things is called depletion. Deep. No, now I'm a bit deep. Where is English-speaking people? Where should I put 2 E's? Deep, I guess here it's 1, yeah, and here also 1. Yeah. And here's N at the end. Yeah. This is depletion, and this is a ground state, yeah? Yeah, this is a ground state. We discuss it afterwards, but don't mix with the thermally excited atoms like we have at ideal gas. So ideal gas, T0, all sit in a condensate, and you have non-condensate only if you hit the system. With interaction, presence of these particles with P non-zero is an inevitable consequence of the interaction. They are there even at T equals 0. If you hit, of course, you get more, but at T equals 0, you have a fraction of this, we calculated, even at T equals 0. Yeah? Okay, so we assume that it's indeed remains large number, macroscopically large number in the condensate. And let's now simplify things in the following way. Yeah? Because if I now have, you see, if you have now the matrix element of the operator A0 acting on our ground state, yeah, that I will get something. Okay, why should I write? So typically we know that the matrix element, so here, okay, A naught, we calculate in front of the ground state. Let's say I have here N0, and here I have N0 minus 1. Yeah, that's the only non-zero matrix element. That is square root of N0. And now if I look at this operator, I get square root of n plus 1. But if this is a macroscopic number, n0 plus 1 and n0 are hardly different. Yeah? So the idea of the method is just replace this with n0. And if you do it, your operator A naught becomes a C number. Yeah? So that means if I do it like this, that means that I neglect unity, which you have here. I just ignore it. So my operators A naught, only A naught, becomes a C numbers. or if you wish, classical field. Yeah? And these things are very, very large. That's what I said. It's exactly this bosonic enhancement that stays in here and determine these amplitudes for the scattering. Scattering among these particles do not have these things, and therefore matrix element here are of order G. There is no bosonic enhancement. So here, for this one, G times N0, and this one just G. And N0 is huge number. So therefore, we can just replace the A naught. That simply means, and that's the simplification for the Hamiltonian. We just replace the A naught and A naught dagger with the square root of N0. On a field operator level, that means that I adjust it in a form square root of N0 plus psi prime, where these things contains all the operators non-zero. So this is called fluctuation. This is a mean field, and this is fluctuations. Yeah? So it's a similar story. So now how can we simplify, therefore, this Hamiltonian? Let's now have a look. How does it help? Yeah? The first term, they don't have A naught. Well, actually, sorry. Let me just do it like this. No, because we want, there are several ways to do it. The simplest, you can have mu, but then A naught has to be defined. So let me do it like this. So we don't have, we just walk with a fixed number of particles. Yeah? And then what we have, the reason that I don't need now to take in this term A naught, because it multiplies with epsilon p, which is 0. Yeah? So here I would also only have sum over p non-zero, epsilon p, AP dagger AP. So here is, we don't have condensate, it's clear, energy 0 of all the particles on the condensate. Now we come to the interesting part, to the interaction, plus G over volume. And of course the dominant term would be when all the momenta here are 0, yeah, then I will have, of course, square root of N0 A to the power 4. Yeah? And having all zeros, nothing wrong with that. Yeah? Because 0 plus 0 is 0 plus 0. I satisfy the momentum conservation. Yeah? So therefore, the dominant term would be N0 squared. Yeah? Then, of course, the next, I just take 3 of them being momenta 0, but then also the fourth one has to be then with 0. So there is no term N0 to the power 3 half. Yeah? Because if whatever 3 momenta are 0, whatever you like, the fourth momenta would also be 0. Yeah? So therefore, the next term comes only with when you have 2 A0 or A0 dagger, yeah? And therefore you have N0 in total, yeah? Because both of them like this. So how many terms do we have there? Okay. So let me start with the strange terms, because they're easy to count. Let me take here 0, 0. Yeah? That means automatically this has to be opposite. Yeah? So if I put P1 plus Q is 0 and P2 minus Q is 0, then automatically what I have is P1 is minus Q and P2 is plus Q. Yeah? So they're opposite. Yeah? And that's exactly these processes. Yeah? You take a particle from the condensate, yeah? you just don't care whether it's n0 or n0 plus 1, yeah, because it's a huge numbers. Yeah, and then you get something non-condensate particles. And for me, it would be convenient to write, so I have a sum over p, and I have a minus PAP. That's sorry, that's actually opposite process, yeah? Opposite. So for the same token, I can put this 0, yeah? So here 0 and here 0. Then here I will have q, and here I will have minus q, yeah? So therefore, the term would be plus AP dagger, A minus P dagger. Yeah? So it's exactly the forward process. And now, one is here and one is here. And how many options do we have? Actually, 4. Yeah? Because we have it, if we have here and here, here and here, and the same 2 pairs with these ones. So I can put either like this, 0, 0, okay, 0, 0, and I can put here 0, 0, and I can put 0, 0. Yes, and it's 4 options. So I have plus 4, and then you can very easily check that what you get here is always AP dagger AP. Well, clear, the Hamiltonian should respect the momentum conservation. Yeah? So Hamiltonian should not change momentum. So here we annihilate P and create P. So here we create minus P and P. And here we annihilate P and minus P. So total momentum is conserved. It's just a check that everything correctly. Then, of course, comes the terms square root of n0. Yeah? But they contain high order. So here, just one of them. And they describe the process where you have 1 condensate particles and 3 non-condensate, so collide with a non-condensate particle. It's a collision between this and this. But here you have already square root of n. Yeah? So therefore, and they are 3rd order terms, and of course there are 4th order terms, which are just like that, where all the momenta are non-zero. But these things we ignore, because we couldn't solve with 3rd order and the 4th order. Yeah? So let's limit to the dominant one, which contains n0 squared and n0. Okay? So therefore, you are walking in a low energy sector of the theory where n0 close to the ground state, where n0 is a very large number. So therefore, you're just looking at the matrix element of your Hamiltonian. Yeah, so it's an operator, and if you take the states, and if you're looking at this corner of the Hilbert space, which is a low energy sector, this is exactly the terms in the Hamiltonian that gives you the dominant matrix elements. Yeah? And that is the approximation. So now I just have to walk with I just remove mu. Yeah? So that makes me a bit easier life for the calculations. I have less equations to solve, to find the minima, etc. But now I have, because I don't have mu, I have n. N is fixed. And in the same spirit, I should write down the expression for the total number of particles, which is n0, yeah, when p is 0, plus sum over p non-zero, AP dagger AP. 20 minutes, yeah? Yeah? Okay. So now, from here, you immediately find that n0 is n minus square root of p non-zero, and here is sum over non-zero p of AP dagger AP. And of course, what I am going to do now, I just want to substitute this n0 into this expression. and keeping only terms which are now proportional to n squared and n, and get rid of all terms that do not contain n, for the reason that I ignore these terms here to be just consistent. Yeah? So let me now think what is, so here I just have, so if I take n naught squared, yeah, so which is this term, yeah, I just prepare some formula. So you get n squared minus 2n sum over p non-zero ap dagger ap plus, of course, the square of the sum. But because I ignore these terms here with the 4 a's and a daggers, yeah, it was like this one with all p non-zero, to be consistent I have to ignore this term here as well. Square, sorry. For the same reason that I ignore these terms here. I even ignore a larger term here. So this I should for sure ignore. Yeah? So therefore, let me plug it in. And see what happens. So what we get? H would be then sum over p non-zero epsilon p a p dagger a p. Then I will have, so the first term, the dominant one, that would be plus g, oh, sorry, I think I forgot here 2, yeah, when I write the Hamiltonian. Please recover the 2, g over 2v. Yeah, sorry. This is this one. Then we will have a term here plus g over 2v. And then from here comes minus 2n. Yeah. This is this one. This one I ignore. So now coming back to this one, yeah, you see if I plug it in this expression here, I will get first term where I have, instead of n0, I have n. And then I have the term which has no n's, but 4 a's and a daggers. And this, again, I have to ignore for the same reason. I ignore it here, and I ignore it there. Yeah? So what you have here, therefore, just the replacement n0 with n. So I will have plus gn over v, sum over p non-zero, and then the rest what stays here, it's 2v, again I forgot this 2. 4ap dagger ap plus a minus, okay, p dagger a minus p dagger plus a minus p ap. So, and now I have to collect the terms. Of course, I have this 1/2. Okay, let me write it. N times 1/2 gn, or whatever you want, whatever you like to write this term. It's like this. And then we have the sum, which is the interesting part. But now it's quadratic. Yeah? And the quadratic form we can always diagonalize. Yeah? So now let's count what we have here. We have here, you see, we have here minus 2n. Here we have 4n, which gives me 2n divided by 2 gives me n. Yeah? So here I will get epsilon p plus gn ap dagger ap. Yeah, so I just combine this term, and this one. And all these things, these two, sum up to gn ap dagger ap. Because I have here minus 1, yeah, g times n, and here I have 2 g times n. And the rest is just what we have here, plus 1/2 gn, and then you have a minus, okay, a p dagger, a minus p dagger, plus a minus p a p. So this is now the Hamiltonian simplified already. And it's quadratic. Yeah. So, and again, it takes into account the particles that sitting in a condensate and the pairs of non-condensate particles with the opposite momentum. So it's exactly the pairs that comes by the collisions of two condensate particles, P0, 0, P minus P, and the reverse. So you ignore all the scattering between condensate and non-condensate and among condensate particles because the amplitude of these processes are much smaller than the amplitudes that are given by this Hamiltonian. Yeah. So it's just physically to understand what is behind this, yeah, what kind of collisions you take into account, which one you didn't. Yeah. Of course, you can do a better job, and people did it, of course, if you want to study, let's say, decay of excitations, etc., etc. You have to take into account all these higher order terms, and after that, like if you study the field theory, that's exactly what it is. You have a quadratic part, and then you have non-quadratic part that determines scattering between particles and imaginary parts and renormalization, mass, etc., etc. Yeah, so in principle, it all can be done because you have weak interaction. You have a controlling parameter here. In reality, of course, it's not so simple, yeah, because if you go to higher order, you have to take into account free body collisions, etc. So, but it's a technical stuff. It does not actually change the picture, the physical picture, just changing the numbers. Although introduces decay, which is also an important phenomenon. Yeah? So how can we proceed? Yeah? You know, mathematics, any quadratic form can be diagonalized by the linear transformation. So let's make a linear transformation, which is called Bogoliubov transformation. So instead of A and a dagger, which are clearly not the eigen, so to say, operators, we introduce the operator alpha p, which is a linear combination of them. Yeah? If you have this, if there would be not operators, just a complex numbers, yeah? You know how to diagonalize. You have to mix z, a and a star, so we therefore have to mix a and a dagger. And this is no problem, yeah, because you see this Hamiltonian does not conserve the number of atoms. Yeah? But one has to be careful in thinking because here you have p non-zero, so it does not conserve the number of non-condensate atoms. In principle, you can all formulate a bit more careful way just to exactly preserve the particles number, but the formalism becomes a bit more heavy, but the consequence would be the same. Yeah? So let's take the easy route. Yeah? So we mix A and a dagger, and we write it like this. So here I write minus p for the reason because I want this to be an operator of excitations with momentum p. Yeah? And if I, okay, let me write a alpha dagger, which is probably easier to interpret, a p dagger plus vpa minus p. Yeah, so here if I create excitation with momentum p, how can I do it? How can I add? So that means I add momentum p to the system. I can either add an atom with momentum p or remove an atom with momentum minus p. Yeah? So that's why it is written like this. Yeah? So this would correspond creation of excitation with momentum p. So you add momentum p to the system by either adding an atom with momentum p or removing an atom with momentum minus p. And you see here I don't put a conjugate. Here in principle I can consider these amplitudes up and vp to be complex numbers. And in some cases I should do it if I want some flow, etc. But for the ground state we can limit ourselves to up and vp being real numbers. You will see that would be enough. If for some reason that would be not enough, we have to extend it to complex number, etc. And moreover, you see I don't put here dependence on the vector. So it depends on the modulus. So, but this is more or less clear. Yeah? So you have a rotational invariance. So it shouldn't be like this, at least if you look at the ground state with, which has total momentum 0. So what I want from these operators, this is not just an operators, I want them to be bosonic. Yeah? And saying that, I have to impose that alpha p and alpha p1 and alpha p2 dagger commute to alpha p2, sorry. A commutator of this is a delta p1, p2. And also that the alphas and alpha daggers commute to 0. That means that my new particles, alpha, or quasi-particles, or excitations, are bosonic. And I can also write, so they have a standard matrix element, what I know. And of course, why I introduce all these things, the idea is that if I introduce them properly, so I choose the proper u and v, which are such that I have bosons, and I want that the Hamiltonian in these variables, so I go back, so give me some energy, which would have the meaning energy of the ground state, plus sum over p, EP, non-zero if you like, alpha p dagger alpha p. So that this Hamiltonian in A, in atomic operators, being transformed to quasi-particles operator, or excitation operator, better say, it has this quadratic form, with positive EP. Then, of course, alpha has the meaning of excitations, because in the ground state, I can define the ground state would be such that all alpha p annihilate my ground state. So there is no excitations in the ground state. And if I add excitation, I add a positive energy. That's the meaning of excitations. You create it and you increase the energy. So that would be my goal, to find such u's and v's that I can bring the Hamiltonian to this form. So let me today have, I guess, time only to work with these things, and the rest, the heavy stuff, we do at the end of the day. It's a very good time to do the heavy stuff. Okay, so let me check whether I can have the bosonic character. Let me look at this commutator, alpha p1 with alpha p2 dagger. Let me have a look what it is. So I just use this definition. I just put it in here, u p1 a p1 plus v p1 a minus p1 dagger. I have to commute with u p2 a p2 dagger plus v p2 a minus p2. So here's a fat comma. So and then, of course, we know the algebra, so the only non-trivial commutator is this with this, and this with this, because A commute with A and A dagger commute with A dagger. So these are only non-trivial commutators, and here you will get UP1, UP2, and then we have a commutator of AP1 AP2 dagger, and then we will have V plus VP1 VP2, but now we have a commutator in the wrong order. We have A minus P1 dagger with A minus P2. So this is, we know, delta P1 P2, but this one is minus delta P1 P2, yeah? Because if minus P1 equals to minus P2, P1 is equals to P2. Yeah? So let me skip here minuses here, minus here and here. Yeah? So you see what you get here. You get delta P1 P2. That's nice. That's what we want to have here. And the coefficient is, because now P1 equals to P2, we have here UP squared minus, because of this minus, VP squared. And of course I can have my bosonic commutation relation if I would have, and this is the first constraint, UP, if I have from here, we have UP squared minus VP squared has to be 1. This is constrained, but still we have a freedom. Yeah? It's a good exercise to check that for this choice of U's and V's, which depends on modulus and real, the other commutators are just automatically 0. You don't have any new constraint that comes from here. Yeah? It's by this choice of the U's and V's. Yeah? I won't check it. I just use the rest for this should remind you, yeah, because in principle, yeah, alphas, fine, we define alphas, but here we have A. Yeah? Principle, we can do it also with A, just we know what's the commutator of these things, yeah, and then we just, well, but it's more convenient and more straightforward to make an inverse, yeah, because we anyway we want to put A in this Hamiltonian, A as a function of alphas, and find the condition when it has this form. So there is no alpha alpha and alpha dagger terms. Yeah, that is our idea. For this we need inverse, and inverse is easy to find if you remember that this is equivalent to something like this hyperbolic relation. Yeah. I can have that this is my UP, some cosinus hyperbolic of some phi p, yeah, and VP is sinus hyperbolic of some phi p, yeah. So this transformation from A to alpha is a hyperbolic rotation. For bosonic, this is unfortunately non-compact things. For fermionic would be compact. For bosonic non-compact, with all these complications that comes with it's a purely comes from these non-compact things here. Yeah, but this tell me if I say, okay, this is my hyperbolic rotation, I know how to do the inverse. I have to rotate on the minus angle. Yeah? So the inverse, therefore, is a hint. Yeah? Inverse is AP. Yeah, remember U was a cosinus. It doesn't change the sign when phi goes to minus phi. Is UP alpha P. And V is sinus hyperbolic, it changes sign. So minus VP alpha minus P dagger, and AP dagger is just the Hermitian conjugate of these things. So this is our inverse. You can check. If you put AP and A minus P dagger, let's say here, then this condition will guarantee you that you get A equals A, or alpha equals alpha. So this is the inverse, and we will start using this inverse in this nice Hamiltonian later today. Okay, so I finished now. If you have questions, then please ask.